Hello everyone, my name is Shambhavi. Hope you all are doing well. So, as discussed in the previous video, we were seeing regarding a test of two variances, right? We had seen many random samples and all the things we had already seen for the two variances, right? Now basically I had even referred you the formula as well. Let me go ahead, go back, and yeah, this was the formula as well that we have discussed out, right? Now, after this particular, we are going to discuss about some more things into this particular topic, right? Now, I have already told you about the n minus 1 and all those degrees, right? Now, I have some more important things to refer out here in a short while. So, yes, now we go ahead from here. So, now I'll be starting up here that if the null hypothesis, hypothesis if the null hypothesis is sigma 1 squared is equal to sigma 2 squared, then then the FR ratio, that is the F ratio becomes, F is equal to, we have S1, okay, 1 second, I would just write that down, the thing down there so that it separates from the other and it doesn't mix up, okay. So if the null hypothesis is sigma 1 squared is equal to sigma 2 squared, then the F ratio becomes, we have F is equal to, from here we have S1 upon sigma 1, right? We have S1 up, okay, yeah, it is S1 squared, okay? And here we have sigma 1 squared, fine, closing this out. Dividing that by, here we have S2 squared, and okay, that's complete S2 squared, and it's complete sigma 2 squared like this, right? I'm closing out the bracket. Now that is equal to S1 whole square, okay, 1 second, I would remove this out. That is equal to S1 whole square divided by S2 whole square, fine. So for the F ratio becomes, F is equal to S1 square upon sigma 1 square divided by S2 square upon sigma 2 square, fine. That is equal to S1 square divided by S2 square, fine. Now this is one of the more formula which we completely use out here. But here is one of the note that you shall keep in mind while using out this particular. So I am just going to mention out that particular note here. So note and putting on the colons, right? This note. So here we have that the F ratio could be, okay, could also be actually, okay. The F ratio could also be, that is S2 whole square divided by S1 whole square, fine. So it depends on HA, that is the alternate hypothesis, okay, and on which sample variance is larger, and on which sample okay, that is variance, VARI, and on which sample variance is larger, fine. So it depends on HA, that is the alternate hypothesis, and on which the sample variance is larger, fine, right. Now other than this, basically we are having some more things which are basically referred out here regarding some of the population and some others as well, so I'll mention them out. Let me get out some space here for writing, then I will proceed on, fine, right here. So I would start that if the two populations have equal variances, variances, okay, if the two populations have equal variances, then S1 square and S2 square are, S2 square are close in value, and F is equal to S1 whole square divided by S2 whole square. Fine. So if the two populations have equal variances, then S1 square and S2 square are close in value, and F is equal to S1 square divided by S2 square. Fine. Now, and it is basically close to the value that is 1. So it is close to 1. Fine. But what happens if the two populations, if the two population variances, but if the two population variances are, but if the two population variances are very different, putting out a comma here, comma, S1 square and S2 square tend to be very different. So if the basic total population variances are different, if the two population variances are different, then S1 and S1 square and S2 square as well tend to be very different from each other. Okay. Now, let's say I choose first of all the S1 square. So here goes our choosing S1 square as the larger sample choosing S1 square as larger sample, variance as larger sample variance causes the ratio S1 whole square divided by S2 whole square. Fine. So choosing S1 square as larger sample variance causes the ratio S1 square divided by S2 square. Fine. And that to be greater than 1. And that to be greater than 1. Fine. Now, if S1 square and S2 square, if S1 square and S2 square are far apart means are basically far from each other, then, okay, 1 second, let me get out again some space for writing. Now, it goes that if S1 square and S2 squares are far apart, then in that particular case, we could say that F is equal to S1 square divided by S2 square. Fine. F is equal to S1 square divided by S2 square is a large number. Okay. Now, therefore, we see that it is close to 1. So, I would just mention that here as well. Therefore, if F is close to 1, therefore, if F is close to 1, so let me just get down out here. Therefore, if F is close to 1, so in that case, we say a little above, I just really want to go. Fine. Therefore, if F is close to 1, so in that case, the evidence favors, the evidence, okay, FAVOR is that is the evidence favors the null hypothesis, the null hypothesis, fine. But if F is much larger than 1, then basically the evidence is against the null hypothesis. Then basically that is not in part of the hypothesis evidence, fine. So yeah, hope I am very much clear with all of these things which I mentioned up here regarding all, 1 second. Therefore, it's IE as well right here. Fine, so hope I am very much clear with all the things which I just mentioned out at this particular place regarding whatever we have studied, for what are the conditions we had applied, and if basically the S1 is this and S2 is this, so what will happen, and all those things. Hope I am very much clear with that, right? So this is all for this video. Till then, thank you and take care.